Welcome to this video where we're going to start working through the OMAE Barge example for a complete hydroelastic analysis. Now, if you haven't downloaded the example files from the website and have access to the OMAE Barge input files, then I encourage you to pause this video and do that now so that you can work along with me. So if you have the OMAE Barge folder open, then you'll see a list of files here. And all these .txt files are input files that we're going to be using. The MPG files are just there for your use to understand the types of videos that can be made from Hydran output. All right, so we're going to start off with looking at workflow for OMAE Barge. And so the PDF file is on the website. So if we go there, this is the workflow for OMAE Barge. So there's some information in here, but we can see that there are multiple steps that the analysis is broken down to. So step 1, and then 2, 3, 4, and so forth. So we're going to go through this step by step, and each step is going to be a separate video. There may be some steps that are combined into one video, but we'll see how it works out. So our first video, this video, is going to just be focused on step 1, which is defining the structural model, and that's very important. So defining the structural model, making the appropriate modeling decisions, and is really where a lot of the engineering comes from, and then it comes into play. And then finally, evaluating the results is also where the engineering comes into play. And a lot of the internal stuff is just done by the program, right? All right, so one of the things that we want to do is we want to look at some of the syntax of Hydran. I'm going to use this video as an opportunity to introduce that. And some of this is explained here, but you can read this as well as I can read it, so I'm not going to go through that, but rather this is eigen.txt. This is the input file that we're going to be looking at first. Now I'd like to point out that I have uncommented the return here. So a // as I mentioned before, means everything after that is a comment. So the program just ignores it. This return here allows us to just go through part of this input file while we check the input, and then we can comment that out to proceed. So this first section here, section 1, define structural model. Again, this is all a comment, right, because of the /*. This just involves down to here, section 2, in other words, to this return, just involves defining the structural model. And then the section 2 involves determining the in-air natural frequencies and modes. We're not going to do that right now in this video, because first we need to create the mesh and do some error checking before we can continue on to calculating the eigenvalues and the vectors. All right, well, let's look at this. So I have a comment here that says begin input. So here I'm just going to be, just for convenience, for changing parameters as need be, I'm going to define some variables that I'm going to be using subsequently. So for example, set I says set an integer variable. And so I'm going to define this variable, number frequencies, and set it equal to a value of 30. Now, this is an easy way of being able to then modify the number of frequencies. Let's say I decide 30 is way too many, I'm going to use 20 instead. I can come back here and just change it right there and not have to look down in the code where it actually comes into play and use it later and change it there. Or I could clearly decide, 30 is not enough, I need to do more, use more, then I can change it. So again, this is a parameter that you're not necessarily going to know a priori, right? There might be some iteration involved to figure out what is an appropriate value. Number of iterations, so the eigenvalue solvers are iterative, and so this just specifies the maximum number of iterations in the subspace iteration algorithm that it's using. There are multiple algorithms that Hydrogen can use, but the default is subspace iteration. And so unless that fails, I recommend that one. Number of digits, that just says, okay, well, how accurate do you want the eigenvectors? So it's going to do it to 10-digit accuracy. Shift, well, so we're going to be calculating the eigenvectors and eigenvalues for a free structure, a structure in air with no restraints, so that we know the first 6 are going to be 0, which means the stiffness matrix is singular. So we need to apply a mass shift, so-called mass shift, to be able to calculate those. And I've found personally the value of 1 to, I've never found a value of 1 not to work for me. So, but you can change it if there seems to be some problems. I'll get to this. This is defining a vector, 1/6 matrix or vector, and I'll get to what that means. And this defines a 1/3, and clearly I think it's kind of obvious that I'm defining where the CG is. So I'm going to be using the inertial coordinate system, which has its origin on the still water line. And we already know from the example that the CG of this body is at 0.5. So 0.5 above the still water line. Remember, we determined the mass distribution to give us that CG. This file, feamesh.txt, is where we actually specify the mesh. And so if we go to that, to the folder, we can see that that file here is present. And so what we're going to do is we're going to look at that file to see what we need to do to specify the mesh. So if I go to that file, let me go to the top. So again, I'm specifying some additional parameters here that are needed for the input of the mesh. So number nodes, again, I'm specifying them here so I don't have to specify them later on the actual command line. I can just reference them using the variable name, number nodes in this case. So I need to specify the maximum, a number that's at least equal to the maximum node number, node ID number. So I'm actually specifying the number of nodes here, but you could specify 6,000 or 7,000 or 10,000. It's fine, as long as it's larger than the maximum node required. The shell element we're using expects 3 moduli of elasticity, just in case we're not talking about isotropic. We're talking about isotropic here, so all the values are going to be the same. This is the 1.5 gigapascals, or actually 15 gigapascals, excuse me. Poisson's ratio, again, expects the 3 values. Shear modulus, again, expects 3 values, but if you calculate use the relationship between shear modulus, Poisson's ratio, and modulus of elasticity for an isotropic material, you'll see that these values satisfy those requirements. So remember, we specified 2 different thicknesses here. The 0.05 is for the in-plane behavior and the mass calculation. The 0.25, I define that to be thick B, bending thickness. By the way, you can use any name you want for these variables. It's just you pick a variable name and use it. Set R says a real variable. So that's 0.25 if you'll recall, and that's to represent the smeared, the additional stiffness from stiffeners that we're kind of smearing it across the plate. I define density to be the bottom plate mass density and density 2 to be the top plate mass density. Remember, they were different to give us the 0.5 location of the CG. And so that's then the end of the input parameters. So the mesh requires us to specify the nodal coordinates and the element connectivity. So first we specify the nodal coordinates. And the format I've used here is what you would typically see if you're generating your mesh in a mesh external program like a mesh generator, and then exporting the nodes and elements for input into HydroNXR. So typically each node would be specified or defined individually. I think the syntax is pretty straightforward. You define the node ID and then the X, Y, and Z coordinates. Here is an example of where I've used the variable that I defined previously. So this command nodes and then pound equal is expecting number equal is expecting an integer value. But instead of specifying the integer value, if you can specify a variable name that contains the integer value that you want to use, if you precede the variable name with the tilde, this tilde here. So this says to the program, okay, go to number nodes and use the value that it has for this input parameter here. All right, so if we come down here, we come down to the end of the node specification. Whoops, here. And we see that there's only 2882 nodes specified. That's because we're only specifying the 4 corners of each shell element. Remember, the shell element we're using here is actually a macro element formed by 4 triangular elements in a cross-diagonal pattern. And the element internally will generate that internal node. And so there's actually going to be more nodes generated. This number plus the number of elements we have. Okay, now we're going to specify the shell elements. And again, this is as if it's been exported by some external mesh generation program, and so it specifies each element individually. So min5s is the element name, the element name within HydroNXR. There are 3 material parameter property sets that we're going to use, and there are 2880 elements. So the first 3 lines are the 3 material property sets. So we need 3 because we have 3 different mass densities. A mass density for the top plate, a mass density for the bottom hull, and 0 mass density for the sides. So I have here as comments here that this is the top deck, the bottom hull, and the sides, front, back. So I think this is clear. We're using the modulus of elasticity specified earlier, the G modulus, the Poisson's ratio, the thickness for the thickness, thick for the thickness, thick B for the bending stiffness. The mass densities are different. Remember the side plates and the front and back plates are 0 mass density. Now this is what I want to look at a little bit here. So if we look at this, I think the syntax for the most part is clear. We specify the node number, we specify the nodes, and we can either use a counterclockwise orientation or a clockwise orientation. I'll get to that in a minute. We specify the material property set number. That's 2. So right now we're specifying, if you'll recall, the bottom hull. All right, so face tells the program which face of the element is wet. So let's come back here to the nodes. So the convention in HydroNXR is if you're looking at the shell element, a face of the shell element, and the nodes are in counterclockwise orientation, you're looking at the positive face of the element. And this is fairly traditional convention in finite elements, structural finite elements. If you're looking at it and the nodes appear in clockwise orientation, that means you're looking at the negative face of the element. So I've defined these elements so that the nodes are counterclockwise when you're looking at it from the fluid towards the structure. So that means face 1, the positive face, is going to be wet. So this is the bottom hole, and so face 1 is specified. That it tells the program that face 1, or the positive face, is going to be the wet face. So the program to calculate the hydrostatic stiffness needs to know what the density of that external fluid is. And so that's what this is here. It's just the density of the fluid. This density is 0 because this, if you'll recall, is the top deck, and there's no fluid up on the top deck. There's only fluid on the bottom hull and the four sides. So that's clear there. So if we scroll down, everything, I defined everything to have the positive face out of the structure. So here we don't have a face, and that means that we're now defining that top deck, right? Material property set 1. And that's all that's in this file. We have a return here. It's, again, the command is terminated. It's frequently these commands that have an indeterminate number of input lines following them. They're typically terminated by a blank line. So we terminate both the element specification and the node specification by a blank line. Return just says, tells the program to return to the calling file. So that returns us back to eigen.txt. So if we come back to eigen.txt, now we've finished that, and pmin5s just says, okay, print to the output file the every element. Sometimes this can be a lot of output, and so you may want to do that, or you may not want to do that, and you can always comment out this line if you decide after a while that you don't want to do that anymore. Similarly, pnodes prints the nodal coordinates for every node, and so that also generates a lot of output. So you can comment out if you want. So the next line says we need to specify the boundary conditions. In other words, are there any restraints to the nodal degrees of freedom? So each node has 6 degrees of freedom, so there's potentially 6 restraints. So in our case, the structure is just in air, free. There are no constraints. And so we specify globally that all of the nodes are free. So 0 means, so this is the x displacement, y displacement, z displacement, x, y, z rotations. So this just says that all the degrees of freedom are free globally for all the nodes. The next input line, node order, just says, and you'll want to use this command if you're dealing with a structure of any size, of significant size. And what it does is it says, okay, go through and optimize the ordering of the nodes for the equation numbering scheme. So that'll be for large structures, one needs to do that to optimize the size of to minimize the size of the stiffness and mass matrices. Form K just says form the stiffness. Form M says form the mass. And now we're ready to do some error checking. So mass summary will calculate for this complicated, not so complicated in this case, but for this detailed structural mesh, will calculate the 6x6 rigid body mass corresponding to the properties specified in this file, in the input file, in the mesh definition. So we can specify where we want to calculate these properties about what point. And so I've said, okay, I'm going to calculate it about the CG. Remember, I defined this parameter, this variable CG, to have the coordinates of our actual center of gravity, at least the center of gravity that our mesh should have. And then dash save just says, well, that'll save that 6x6 matrix in case you want to use it later for some purposes. If you don't care about using it later, then you don't need to include that. And finally, we have this export graphics command. I'm exporting to in .msh format that can be read by, say, Gmesh or some other program that you might need some post-processing of that file that you can read. But it can also be read by the GUI of HydroNXR. And I'm specifying here the name of the file, so it's just feamesh.msh. The .msh is necessary. You need to add that extension. If you're using, say, dash techplot here as one of the options for export graphics, then this would be .dat. I should add that it's likely that in future versions of HydroNXR, I'm going to deprecate the use of dash techplot here because I don't have access to techplot anymore, and I cannot verify that the output from this program will be consistent with any changes made going into the future in techplot. So I'll probably deprecate it. Now here I say return. Okay, so this is an intermediate return to allow model inspection prior to continuing, as I mentioned before. So we're going to first have a return here, so we're going to stop processing so we can evaluate the results and make sure that there's no obvious errors. And then we'll come back and we'll comment this out so that we can proceed then on to determining the in-air natural frequencies and modes. And then we also need to do some error checking there, of course. I would like to come back here to the mesh generation. Now this is a very simple structure, and so actually one could have generated the mesh within Hydran itself, because Hydran does have, for simple geometries, some mesh generation capabilities. So let me come to the folder here, and we see that there's this FEA mesh-generate.txt file. And that's an alternative file we could have used to define the mesh. So instead of, we could have said FEA mesh-generate.txt to use that file to generate the mesh. So let's look at that file and what it says. So this is just a box, a rectangular box. So there's 6 sides. Really all we need to do is generate the 8 nodal coordinates, specify the 8 nodal coordinates for those for the edges of the box, the corners of the box. We still need to specify a sufficient number here that's going to cover, be at least as large as the maximum number of nodes that we're going to, maximum node ID that we're going to have in our mesh. So then we can come down here and where we specify the elements, we still need to specify the 3 material property sets, but then we really only need to specify the 6 sides, the top, bottom, and the 4 sides. And so what I've done here is I've just specified one element to represent each of those 6 sides. One element for the bottom hull, one element for the top deck, the side that's at the positive y-axis, the side that's in the bottom, negative y-axis, the bow, and the stern. And then I can tell the program, okay, go ahead, go in and subdivide, in this case, elements 1 and 2, the top deck and the bottom hull, into 10 by 100, into a 10 by 100 mesh. And similarly, the elements 3, 4, the 2 sides, I tell it to generate, to subdivide them into 4 by 100 meshes. And finally, for the bow and the stern, I tell it to generate or to subdivide into 10 by 4 meshes. So whether it's 10 by 4 or 4 by 10, you need to look at the manual to understand which order. Basically, it generates it along the x-axis, the local x-axis first, and then the y-axis. So let's come to running this example. Now, I've mentioned before that, let me go back to the eigen.txt. So I mentioned before that there are two options here. We can run it in the GUI or we can run it in the terminal. And I've decided that for the most part I'm going to be running in the GUI. I'll run it in the terminal once or twice probably just for demonstration that we can do that. But for the most part I think I'll run it in the GUI. So let's start the program. And it opens up on my other screen all the time, so because that's my main screen. So it all opens on the main screen. So if you've run HydroNXR before, then this is gonna be populated with your last the last project, and here there's going to be a drop down of some previous projects. I think up to 10 previous projects. In this case, I've only run the one. So if you're running it for the first time, then you'll need to specify the project folder, and the project folder is where the input file is. I'm going to cancel that because I already have the correct project folder. And then the project name, my convention is to just use the input file name as the project name. The main input file name is the project name. For the most part, we'll see when that is not convenient. Okay, so that again, all these windows open on the my main screen. So this is the first screen you'll see, and you'll see that it's created eigen.log and eigen.out. So if we go to the folder, we can see it's created eigen.log and eigen.out. Eigen.out is where all the output data is written, and eigen.log is just a record of every command that's been issued. So you can run eigen.log to recreate an analysis, a sequence of analyses if you want. I don't use it too often, but sometimes it might be convenient. All right, let me, well, before I hide this, actually, I want to comment that HydroeXR creates a lot of files with the project name and then a lot of different extensions. We see here that there are already 3 files with the same name but different extensions, and there's going to be more. So I know Windows and Mac both have the option of hiding file extensions. I don't think it's a good practice, and especially if you're using a program like HydroeXR, and there are a lot of programs out there that generate a lot of files with the same name but different extensions. So I think it's important to make sure that you're viewing the extensions so you know which file you're looking at in this sort of directory. So okay, let me hide this for right now and come here. I'm going to file in our input file. So I'm going to use the file in command as we saw before in the input file itself, which filed in yet another file. But before I execute this command or submit this command, if you have a question about the syntax for a given command, you can come to the PDF reference file, which is here, and look at the syntax, find the syntax for the given command here. So you can either use a search command if you want, or let's say we want to know what the syntax for file in is. We can then click on there and it gives us then the syntax. And we see that, okay, there's an optional file name. If it's in brackets, something is in brackets, it means it's optional. So it's the file name is optional, as is this parameter no echo. We're not going to be using that. So I'm not going to, as you notice, I did not include a file name in this over here because if the file name has the name of the project, it'll take that automatically without having to specify it. So I could say file in space eigen or file in space eigen.txt. It adds the .txt automatically. but it's unnecessary, so I don't usually do that. Of course, also you could use the help.out file, that text file, which is typically what I actually end up doing. If you have a question about, you don't quite remember the name of a command, you know which command you want to use, you don't quite remember the name of the command, you can start typing and then control space will bring up all the commands which begin with whatever letters you've already started typing. So I can see that it's file in there, and I can click that one and use that. So I am going to hit enter here, and we see the input file gets processed. We see that we have generated the 6x6 mass matrix here, and so we need to make sure that these numbers are correct. We know from before that the total mass of this box is 1025. That's the displacement, and so we know the mass also has to be that same value. So 1025 tons, and so that's what we have here for the X mass, the Y mass, and the Z mass. The zero off diagonals here tell us that that we're doing it around the CG, so our calculation of CG is correct. But also I notice that I point out here that the center of mass relative to our input point here is calculated, and it's calculated to be 0. So that tells us that the center of mass is indeed at 0.5. The mass moment of inertia in the x direction around the x-axis, y-axis, and z-axis are here, these diagonals. And of course you should know what those are and confirm that the values you have here are within acceptable numerical errors, the exact values, or the values you would expect. The zero off diagonals here tell us that we're working with our principal axes, inertial principal axes. So, and then we see that we've processed this command as well. So we've confirmed that our mass distribution for our structural mesh is correct, and now we need to make sure that the mesh looks right. It's a very fundamental check of our mesh. So it has created this .msh file, and under View Mesh, we can open that up. And select it for opening within HydroeXR. Now you can also open it up in another program like Gmesh or some other program that'll open .msh files. So we open it up, and we end up then with this, and using the scroll wheel we can, and the mouse we can zoom in, we can shift the location, and we can rotate it and look at the top, the bottom, the sides, and make sure that there's nothing fishy about this guy. And we look good. So at least this cursory view of the mesh looks good. And so maybe we have confidence we can continue. So the next step, of course, is to calculate the normal modes and natural frequencies in order to create our reduced basis. So that will be in the next video.